Greetings to all and welcome to this lecture. We are in module 1, review of semiconductor fundamentals, and lecture number 3, carrier transport. In this lecture, we will see how the charge carriers, it means the electrons and the holes, will move in the semiconductor. Broadly saying, there are two phenomena in the semiconductor which captures the carrier transport, that is carrier drift and carrier diffusion. These are the learning outcomes of this lecture, which tells you that how the carrier transports in semiconductors, including drift under the electric field and diffusion due to concentration gradient. This lecture will help you to plot the conduction band and the valence band slopes with varying the electric fields. Let's do a quick recap. In the previous lecture, we understand the fundamentals of semiconductor in terms of charge availability. In the sense, we said that there are two types of charge carriers available in the semiconductor. One is N and one is P, where N is nothing but electrons and P stands for holes. We have seen the band and bond model of silicon to understand how these electrons and holes comes into picture. We analyze the intrinsic semiconductor, where we said that Ni square is nothing but Nc into Nv exponential of minus Eg divided by Kt, where Nc and Nv are the effective density of states in conduction band and valence band respectively, with a unit of centimeter to the power of minus 3, where Eg is the band gap of silicon or any semiconductor, and Kt is thermal energy. It means Kt over Q is nothing but phi t is nothing but 26 milli electron volt, right. We have also seen that how to calculate the electron and hole concentration in a semiconductor. So we need to consider the proper limit from the edge of conduction band to infinity, and we take the effective density of state, we take multiplied with Fermi Dirac function over energy, right. This will give me the total number of electron in the conduction band, and the total number of holes in the valence band can be extracted as minus infinity to EV GVE into 1 minus of Fe, where 1 minus of Fe tells me the total number of available state which is not occupied by the electron. We have also seen the charge neutrality equation in the semiconductor, how the charges are neutralized in the semiconductor, and hence under equilibrium there is no current flows into it. We have also seen that how the Fermi level moves along with the doping. If you increase the doping in an n-type semiconductor, the Fermi level goes near the conduction band, and if in p-type semiconductor we increase the doping of acceptor atoms, then the Fermi level goes near to the valence band. In addition, we have also identified how to calculate the difference between the intrinsic Fermi level and the Fermi level. This is important when we are actually dealing with MOS transistor modeling. In this lecture, let's discuss about the carrier transport, how the carriers in the semiconductor can be transported from one position to another. In a very layman word, if you have 2 points A and B, by some means in the sense either it can be this mean, that mean, this mean, or this mean, right. So by some means, if you move the charged particle from A to B, it will give rise to current. So ultimately we will discuss a few more means how can a charged particle will move from one position to another position, and this is resulting a current, out of which the first is drift. It means if you apply a voltage which exerts an electric field in the semiconductor, then the charged particle will move in the semiconductor based on this electric field. This phenomena is called drift. The another aspect is, even if you are not applying external field, but you are maintaining a difference between the concentration. So here you can see here the yellow particles, let's say these are electrons. So the electron concentration here is more and the electron concentration here is less. So the particles will move from higher concentration to lower concentration, and if the particles are charged particle, it gives rise to a current. You can take an example of smoke particles, you can take an example of fragrance, so it will go from higher concentration to lower concentration. But if I give a charge to that particles, it will give rise to a current. So in the semiconductor, if these particles are charged, it means either N and P, and by some mean if I create a concentration gradient in the semiconductor, then these charged particle will go from higher concentration to lower concentration and give rise to a current. That current is known as diffusion current. So in general, this drift and diffusion are basic building block of carrier transport phenomena in semiconductor. There are few carrier transport mechanisms like thermal transport, under which we can talk about Seebeck effect and Peltier effect. It means if you have two regions where you are actually creating a difference between the temperature, then there will be a current flows. That is what Seebeck effect. And what is Peltier effect? If you are actually applying a biasing or the voltage externally, then there will be a temperature difference. So this comes under the thermal transport, which we are not going to discuss in this course. The another is tunneling. This is a quantum phenomena which says that if a charged particle do not have enough energy to surpass the potential barrier, then there is a possibility that the charge carrier will tunnel through this potential barrier. So this is purely a quantum phenomena, and it violates the classical theory. Classical theory says that if this particle, let's say a ball, needs to go at this side of the hill, then this should have this much energy to surpass the barrier. But there is a possibility that the ball can tunnel. This can be defined by quantum mechanics. So again, in this course we are not going to discuss about the tunneling, and we'll only focus on drift and diffusion. Let's start to understand the drift first. Before that, how the charge carrier will move in the semiconductor. So if you have a semiconductor specimen, then you can say a charged particle is moving randomly. It can move this side, you cannot predict its motion. So you can say the charged particle is doing a random thermal motion. Now definitely this charged particle will interact or scatter by something. What that something means, maybe it is a ionized particle, maybe the carrier scattering, or maybe there is a phonon scattering. Phonon means the lattice vibration. So before the scattering, if the charged particle travels this much distance, this is known as free path. And the time it takes to travel this much distance before two successive collision is known as free time. And we calculate the average of this, it will give you mean free path and mean free time. So ultimately, if you calculate what is the velocity of these carriers in the random thermal motion, you can find out by LC by tau c. And for silicon, if we calculate, this value is 10 to the power of 7 centimeter per second, meaning the electrons in the semiconductor is moving with a very high velocity. So you can say it is an intense motion, but the intense motion will not give you the current. The current will be resultant of a directed motion. So the average motion, the average velocity of these carriers under equilibrium is 0. It means they are not directed in particular direction. Now what if you apply a voltage in this specimen? If you apply a voltage in this specimen, then the carriers will move in the directed, and the carriers will do a directed motion. So the directed motion superimpose over the thermal motion and hence give rise to a current. Before moving into the drift, let me introduce a notion of transit time. Let us consider a specimen bar where at this side we are injecting the electrons and this side we are collecting the electrons. We are assuming that there is no recombination and no collision here. So whatever be the electrons just started from here and it will ended up here. So if I want to calculate what is the time travel by the electrons between this position, that time is called transit time. So I can simply find out this transit time as Q by I, where Q is the total charge available in this strip. So you can calculate the total charge here, which is nothing but, let's say this dimension is A, this dimension is B, and the thickness is C. So the total charge is nothing but N. It means the number of electron concentration times of Q. It becomes charged particle. Now A into B into C. So the total charge per current will give me the time taken to travel the electrons from this position to this position, and that will give you a notion of transit time. Let's discuss about the drift part. As I mentioned that electrons are in random thermal motion and the average current is 0. So in the random thermal motion the net current will be 0. But what will happen if you apply a voltage in the specimen? Then there will be a directed motion. To understand the drift and diffusion, let us consider a specimen of a p-type semiconductor having a p-type doping and represented by P. Let us consider this dimension as X and this dimension as Y. The concentration of this p-type bar, so this is p-type semiconductor, the concentration of p-type is P. Let us consider a plane of observation. Plane of observation. So along the plane of observation, if a particle or a electron is coming in the distance LC, LC is what? Mean free path. So though it is a very small value, but consider in a significant scale that this is a LC. It means a particle which is inside this, it will definitely cross the plane of observation, right, without collision. So mean free path tells us the motion of electron without collision, or before two successive collision, how much distance it traveled, the electron traveled, right. So this is LC. Similarly, we are assuming that this is LC. So if a particle reside in this strip, right, then definitely it will cross the plane of observation. So how much particles are there in this strip? It is P into LC into area. This is the total particles available in this strip, and we are actually observing the movement of these particles across this plane of observation. So this is what the total particles. Now if we consider this is only a 2D structure or only 2D analysis, then the per unit area, the total particle will be what? So total carriers, right, per unit area, then it will be P into LC, correct. Now we are assuming that as the carriers are doing a random thermal motion, so 50% probability is the carriers will move in this direction and 50% probability that the carrier will move in this direction, and hence the total charge which crosses the plane of observation is PLC divided by 2. Now can I define the flux? What is the flux which crosses from left to right? So I can simply write flux crosses from left to right is nothing but the total carrier per unit time. So P into LC divided by 2 into now tau C. Tau C is the mean free time. LC by tau C is nothing but what? V, velocity, divided by 2. So this is the flux which is going from left to right, and similarly considering the average velocity or net flux is 0, then the left to right and right to left flux is same. So ultimately the overall net flux will be 0. So if I want to calculate the current density, this is current density, I need to multiply with Q in flux. That will give me a current density. Now let us analyze the two cases. Case number 1, we are assuming that the concentration in this strip and the concentration at this in this strip at the right hand side is not same. It means this side the concentration is P1 and this side the concentration is P2. So what is the flux? Flux will be P1 minus P2 divided by 2 into V, and hence you will get a net flux. There you cannot say the net flux is 0. So net flux will not be 0. So the net flux is P1 minus P2 into V. Case 2, consider the semiconductor specimen is uniformly doped, but you applied a voltage. by applying a voltage, the velocity of the carrier at this side is different and the velocity of the carrier at this side is different. Let us consider the velocity of the carrier at this side is V1 and this side is V2. So here the net flux again will not be 0 and it can be given as what? P into V1 minus V2 divided by 2. So this is basically diffusion, where even you are not applying the external voltage, there is a net flux because of the concentration gradient. That is what is called diffusion. Similarly, this is called drift. In the uniform sample, if you apply a voltage, then because of that there is a velocity difference and hence you will get a net flux. The net flux will give you a net current. So let us analyze again in some formulation. Let us consider a piece of sample and having this dimension A, width is B and height is C. So what is the total charge is here n times Q into A into B into C, where this is a total charge available into the strip. Now if I am interested in what is the charge per unit area, so area in the sense if you see from the top, the area is nothing but A into B. So the total charge per unit area can be classified as N into Q into C. This is the notation we are going to use throughout the course, which says that if Q dash is written, it is nothing but the charge per unit area. Again, in this structure, what is the transit time? So the transit time can be defined as this A divided by Vd. Correct? This is a transit time, total time taken from this side to this side by a carrier. Now if I want to write a current equation, the current equation is nothing but total charge by time. It means N into Q into ABC divided by A into Vd. So if you write, this can be written as N into Q into B into C into Vd, where this Vd is a drift velocity. Drift velocity means a directed velocity which can be provided by the applied voltage. This equation can be rewrite in terms of charge per unit area, where N into Q into C is nothing but charge per unit area. So I can be written as B into Q dash into Vd. Right? So this is a drift velocity which is nothing but directly proportional to applied electric field. The moment you apply the voltage, right, there is an electric field exists and hence the carrier starts to move with some velocity, with some directed velocity, that is called drift velocity. The question is, if you go on increasing the electric field, will the velocity increase? Answer is no. To analyze this, consider an analogy. Let's say a person is flowing in an aeroplane and it will jump from the aeroplane. At the starting point, the speed or the velocity of that person is very high, but when it will jump using a parachute, then what will happen? After a certain time, the velocity of that particular parachute or a person is constant, because the gravity is working in this direction, the friction, air friction is working in this direction, and two forces counterbalance this, and the velocity seems like a constant velocity. That is what is happening when the carrier moves in the semiconductor. You do have an electric field, but there is a collision mechanism also involved, and hence when the carrier moves, it is attaining a constant velocity. If we plot Vd versus E, then we'll get this kind of curve, which simply says Vd is directly proportional to E in range of lower electric fields, but at a higher electric field, this drift velocity gets saturated. This having a more important notions when we talk about MOSFET and the MOSFET modeling. So this proportionality constant can be removed as Vd is equals to mu into E, where mu stands for mobility. Mobility is the ability how freely an electron can move. So in general, if we talk about electron, we write mu n. If we talk about hole, we write mu p. the mobility of electron is higher. You can see here the mobility of the electron is higher than the hole. The rough value for silicon is 1450 centimeter square per volt second for silicon, and this is around 450 centimeter square per volt second. Now you see, if you increase the doping, then the mobility will fall, because the carrier will interact with dopant atoms, and hence the mobility will fall. You can say the ability of the electron to transit from one position to another position will reduce, because in its path there is dopant coming into picture, correct? Now we can rewrite these equations by following this: I is equals to B into Q dash into Vd. I is equals to B into Q dash into Vd, where Vd is nothing but mu into electric field, and electric field is nothing but the applied voltage by A. You can check with this. The applied voltage V by A is nothing but this V by A is nothing but the electric field. So if we are talking in general case, then we can rewrite this as B into Q dash into mu d psi by dx. It means how the potential changes along the x direction, right? If we consider a sample and how the potential changes along the x axis, so this is x axis and we need to differentiate a small strip. So this is a general formula for drift current. By using the transit time notation, we can calculate tau also. Tau is nothing but Q by I, where this is N into Q into A into B into C, and B equation can be written as B into mu B into V into V by A, right? If you see that this B and B get cancelled, this becomes A square and this become Q dash, N into Q into C, and mu B into V. So you will get tau is equals to Q by I. So ultimately Q dash will get cancelled and you will get A square by mu B into V. This is a transit time related to drift phenomena. Now let's talk about conductivity and conductance. In general, we know the Ohm's law is written by V is equals to IR, or I is equals to G into V, where G is nothing but conductance. We can simply rewrite our equation as I is equals to mu B into Q dash B by A into V, or we can simply rewrite as I is equals to G into V, where G is nothing but mu B Q dash B by A, where mu B stands for bulk. Again, we are going to use this bulk mobility, surface mobility in our subsequent lectures. So bulk, so we are not specifying here what we are talking about either in terms of electrons or holes, it is a bulk mobility. So this is a conductance. Now how can you calculate the conductivity? So conductivity is nothing but G is equals to sigma into Bc by A, and sigma is nothing but mu B into N into Q. So the conductivity of a semiconductor is depend on the mobility as well as the electron concentration. The inverse of this conductance will give you what? The resistance, and hence the resistance can be written as 1 over G, which can be written as Rs. So Rs here is mu B into N inverse, right? It is called sheet resistance. What it means is, for example, you have a specimen like this where this is B and this is A. In some cases, if A is greater than A is equals to B, then this from the top it seems like a square, right? So we can simply relate our resistance or conductance in terms of square. So this is what is called sheet resistance in terms of ohm per square. It means if we really want to calculate the total conductance and total resistance, we need not to bother about the specific values of A and B. We can simply calculate in terms of ratios. For example, this is 3A and this is B. So ultimately the length to width ratio, if it is 3, the sheet resistance will be 3 times of Rs. Similarly, if the device dimension is small enough but the ratio is maintained, then also the sheet resistance will be similar. Let's talk about the diffusion. As we pointed out that even if you are not applying the voltage in the specimen, then due to the concentration gradient there will be a charge transfer. For example, by some sense we are maintaining that here the electron concentration will be more and here the electron concentration will be less. So if we plot electron concentration along the x-axis, then we will get a linear fall. This fall can be a non-uniform or non-linear as well, but for the simplicity we are assuming that nx is linearly varied with x, correct? So to understand the diffusion part, let us consider the same example. This is plane of observation and we have LC and this is LC. So mean free path where the electron definitely will be not collide and crosses the plane of observation. I am taking a center point here and this is again what? LC, because I am taking just a midpoint. So here I am considering the concentration is P1 and here I am considering the concentration is P2. So along the x, let us consider it is linearly fall, right? So I can simply write P1 minus P2 divided by minus of LC is nothing but dP by dx. This will give me the concentration gradient, and now again I will go back and I will put in my equation that F net is nothing but P1 minus P2 into V divided by 2. So P1 minus P2 can be written as minus V by 2 into LC into dP by dx. Here if I want to write in terms of current density, it is Q times of F net. So this will be minus Q into V into LC divided by 2 into dP by dx. This parameter can be defined as diffusion constant. As we are talking about holes, so we can write dP, and if we are talking about electrons we can write as dN. Here few are the equations, formulations with respect to same analysis, that we do have a sample and this dimension is A, this dimension is B and this dimension is C. So the total current is nothing but diffusion constant. You can use this, where current density is nothing but what? Current by area. So current is nothing but what? A times of this quantity. So the total current is nothing but D times of Q times of area. So area of this you have to take, where the electrons will go from left hand side to right hand side towards the plane of observation. So this is nothing but what? B into C into minus dN by dx. This relation between the diffusion constant and the mobility is called Einstein relation. So again I am not going for the derivation of this, but this is a useful relation to replace the diffusion constant and the mobility at suitable places. We can simply write the charge per unit area if we assume a small strip of delta x and we calculate the charge per unit area as minus q times of nx into c, like what we have done in our analysis of drift. So all in all, the overall current equation can be given by mu b into phi t, which is nothing but a diffusion constant, b into dq dash by dx. It means the current of the diffusion, the current due to diffusion dependent upon the gradient of charge. In this analysis we have assumed that the charges are exactly at near the surface, but this theory is applicable if the charge is non-uniform in the vertical direction also. It means in the vertical direction if the charge diffuses, then also this theory holds good. For the sake of simplicity, let us consider the total change in charge along this is nothing but linear. Even though the charge is non-uniformly varies vertical direction, it is linearly varying in the horizontal direction. To understand this, what we can think like we have a slices like this, one slice, another slice, another slice and all. Though the charge is non-linearly varying in the vertical direction, it linearly varies in the horizontal direction, and we can assume that is a laminar flow of the carriers happens. To do that, we can consider the dqi by dx is can be written as q dash A minus q dash 0 divided by A, which is nothing but q dash A is the charge at point A, q dash 0 at charge at point 0, and this is the dimension. So we can rewrite the current equation in terms of this. Here the total charges can be given by AB into the average of this charge, and we can simply calculate the tau by Q by I. By using this and putting a boundary condition considering that a pure sink is available at the right hand side, it means the electrons which is originated at the left hand side of that specimen, it actually ended up at the right hand side. So by considering this, we will get a transit time under diffusion condition. So all in all, the total current in the semiconductor is can be given by the sum of drift current as well as diffusion current. In general, we have 4 components of the current: electron drift, electron diffusion, hole drift and hole diffusion, which we will see in our next lecture when we will talk about p-n junction diode. Let us consider you have applied a electric field in the specimen having a non-uniform doping. It means if the doping is non-uniform, then how the electric field changes in the semiconductor. So if you applied the voltage, then this is nothing but what? Electron potential energy. And when you applied a voltage, remember that the electronic voltage varies oppositively to the electron potential energy, meaning if this end is negative, then the potential energy will be higher. If this end is positive, then potential energy will be lower. This will help you to understand the MOSFET physics and the band bending when we will talk about the MOSFETs. So here it is an n-type semiconductor where Fermi level is close to the conduction band, and when you are applying a voltage, ultimately because of the transport, there is a EC minus EF gap is increasing. So how can you calculate the total potential here? The total potential is nothing but the slope of this or the difference of between EC minus EF. So the potential is can be written as EF minus EFI. We can simply rewrite, because of this potential there is an electric field exists in the semiconductor, and that electric field is can be given as minus d psi by dx, which is nothing but minus d by dx into, here you need to differentiate, so minus of EF minus EFI over 1 over q. So electric field in the x direction is nothing but 1 over q dEFI divided by dx. So in a simple sense, the gradient of intrinsic Fermi level or the gradient of EC and EV gives you the electric field in the semiconductor. For example, you have a uniformly doped semiconductor, a non-uniform doped semiconductor, where exponential of EF minus EFI by kT, right? So how can we extract the overall electric field dependent upon this? Let us consider an n-type semiconductor where we can write N0 is equals to Ni exponential of EF minus EFI by kT. This N0 for n-type semiconductor is nothing but what? Nd, and as it is varying along with x, you can write Ndx is nothing but Ni exponential of E minus EFI by kT. So we can simply rewrite this equation as E minus EFI by kT is equals to log of Nd of x by Ni. To calculate the electric field, we need to differentiate and take 1 over q. So it is nothing but dEFI by dx with 1 over q with a negative sign will give you kT over q d by dx of log of Ndx by Ni, and ultimately this equation will give you the total electric field in an n-type sample with a uniformly doped semiconductor. Let's do a brain buzz. Let's see this problem which says that consider a doping varies linearly in the semiconductor sample. So let us consider you have a semiconductor sample where the doping varies linearly, and this is an n-type sample, right? So you need to prove the net current is 0 if the semiconductor is in equilibrium. Ultimately you need to prove J net is equals to 0. So we can start with our basic understanding. The net current is nothing but drift current plus diffusion current. So diffusion current, and that we need to prove at J is equals to 0. So we will start with J drift plus J diffusion. J drift can be written as N into Q into mu into E, plus this can be written as Q into dN by dx. Now this N, as it is varying with respect to x, we can write Nd of x, because electron concentration in an n-type semiconductor can be written as Nd into Q into mu into E is nothing but what? 1 over Q dEFI by dx, like we have seen here, right? So this is E plus Q. Now D, by using Einstein relation, we can replace as mu into phi t into dN dx by dx. Here if we see, this can replace, the electric field can be replaced as this, right? So we simply replace N dx into Q into mu into minus of phi t by N dx into dN dx by dx plus Q into mu into phi t dN dx by dx. If you see here, this get cancelled and this term is exactly cancelled by this term, which means the net current in an equilibrium, even if having a non-uniformly doped semiconductor, is 0, meaning even though the diffusion component exists, there is an equal and opposite drift component exists, which makes the net current equals to 0, and hence your semiconductor is charge neutral in an equilibrium condition. So let me summarize. In this lecture we have seen the drift current is proportional to the electric field and diffusion current is proportional to the charge carrier gradient. We have also seen what is the notion of transit time. We have seen how the band bending or how the Fermi level varies along with the dimension of the semiconductor if there is a non-uniformly doped. The final conclusion we drew is the net current in the semiconductor is 0 when it is in equilibrium. So we will stop here for today. Until then, take care.